Welcome back to my YouTube channel or Davig Structure Hub. This is a place where you learn, build, and innovate. I want to start talking about reinforced concrete design to BS 8110. And into today's lesson, as somebody who is following me, at the end of the session, you should be able to, number one, you should be able to know all symbols used in concrete design to BS 8110. Number two, you should be able to differentiate between singly reinforced beam and doubly reinforced beam. And number three, you should be able to differentiate between a T and L beam. And the last one, you should be able to understand formulas used in design of singly reinforced beam. Now, I will begin by symbols. So these are the symbols used in design of reinforced concrete to BS 8110. As a learner and someone who is practicing civil engineering, you should be able to know these symbols because we are going to use all these symbols for the entire topic. So I will begin by number one, which is geometrical properties. We have B. B is the width of section. D is the effective depth of the tension reinforcement. H, overall depth of section. X, depth to neutral axis. Z, lever arm. D prime, depth of compression reinforcement. And then L, effective span. C, nominal cover to reinforcement. We proceed to number two, which is bending. FK, which is characteristic load. GK in capital or GK in small, characteristic dead load. QK, characteristic imposed load. WK, characteristic wind load. FK, characteristic strength. FCU, characteristic compressive cube strength of concrete. FY, characteristic tensile strength of reinforcement. And this one, partial safety factor for load. Also this one, partial safety factor for material strength. K, coefficient given by M is over FCU BD square. We have K prime is coefficient given by MU divided by FCU BD square, whereby 0.156 is equal to 0.156 when distribution does not exceed 10%. M, design ultimate moment. MU, design ultimate moment of resistance. S, area of tension reinforcement. A prime S, area of compression reinforcement. Then this one is the diameter of the steel, and this one is the diameter of the link. We proceed to shear. Shear, we have FYV, characteristic strength of the link. SV, spacing of link along the member. Capital V, design shear force due to ultimate load. Then small v, design shear stress. VC, design concrete shear stress. ASV, total cross-section area of shear reinforcement. We proceed to the last one, which is compression. B is the width of column. H, depth of column. LO, clear height between end restraints. LE, effective height. So we have LEX. This is the effective height in respect of XX axis. And then we have LEY. This is the effective height in respect of YY axis. Then we have N, design ultimate axial load. Then we have AC, net cross-sectional area of concrete in a column. And then we have SC, this is the area of longitudinal reinforcement. So that marks the end of the symbols, and you should know these symbols all of them. We proceed to tables. I will begin by table 3.1 in BS 8110. So this table is for strength of reinforcement. So we have reinforcement type and characteristic strengths of that reinforcement in Newton per millimeter square. So we have two different types of reinforcement. Number one, we have hot rolled milled steel. The strength of hot rolled milled steel is 250 Newton per millimeter square. And then we have the high yield, 500 Newton per millimeter square. We proceed to another table, which is a table also, it is also a table 3.1 in BS 8110. And this table is for concrete compressive strength class. So the first column is for concrete strength class, and the second column is for designated concrete. And then the last column is characteristics cube strength FCU in Newton per millimeter square. So this table is self-explanatory. Maybe I can explain the first row. We have class 20/25, reinforced concrete 20/25. So the strength class, no, the characteristic cube strength is 25 Newton per millimeter square. It apply to the rest of the remaining rows. So we have another table, which is table 2.2 BS 8110. So this table provides values of safety, partial safety factor for ultimate limit state. So we have the material or stress type, and then the other side you have the partial safety factor. So reinforcement, we have 1.15, concrete flexure or axial load 1.50, concrete shear strength without shear 1.25, concrete bond strength 1.40, concrete or others, example bearing stress greater than 1.50. Then we come to loading. As you know, it is not possible to apply statically principle to determine characteristic dead load, GK or imposed load or a wind load because there are insufficient data. Therefore, the characteristic loads are taken to be those given in the following document. So these are the documents which will provide you with the loading for different buildings depending on its use. For example, we have classrooms, residential building, commercial building. So all the loading for this building is obtained from this document. So number one, we have BS 648. So that is the weight for building materials. So at times we may want to estimate the weight of a material like bricks or stones. So what you need to do is to go and check the values of those weight for such a material in BS 648, and you will be able to estimate the weight of that material. And then number two, we have BS 6399. So that one will provide you with design loading for building. For example, we have part one, it will give you dead plus imposed load. And then part two, it will give you wind load. And then part three, it will give you imposed roof load. For example, like snow. You know, snow can add a weight on a structure. So you have to consider that the weight of that snow when designing a structure, so that it Let's continue. So let's talk about design loads. So design load is given by safety factor for load times characteristic strengths, whereby the values of safety factor for loads for various loads combination are given in table 2.1 of BS 8110. So this is the table. It is divided into load combination and load types. Under load types, we have dead, imposed, and wind. And dead is divided into adverse and beneficial, the same as to imposed. So if you can start the load combination, number one, we have dead and imposed. So in adverse, you use this value 1.4, and in beneficial 1.0 for dead load. And then for imposed, we have 1.6 in adverse and beneficial 0. So no wind for this number one. You go to number two, dead and wind. So dead in adverse is 1.4, and then in beneficial is 1.0. So there is no imposed here. And then you have the wind 1.4. We proceed to number three. You have dead plus wind plus imposed. So all of them are 1.2. All of them are 1.2. And if you are pursuing a diploma in civil engineering, or you just did your diploma, I know that you may not be aware, but this is the reality. You cannot design a 3-story building and above. You are only allowed to design a 2-floor building. So it means you will only use dead and imposed load only. So for design load, it will be 1.4 GK plus 1.6 QK. So this is your area. You should be using this formula for load combination. The same as to those who are pursuing higher diploma in civil engineering or structural engineering. For you guys, you are only allowed to design a structure up to a 4-story building. You are not allowed to go beyond 4. So it is 4 and below. And also, for you, you cannot consider the aspect of wind in your design. So you will only use this formula, which is 1.4 GK plus 1.6 QK. Only for those who are pursuing degree are allowed to design a 5+ story building. So it means they will use the aspect of wind loading, because above 5 stories you will consider wind loading in your design. So that is all about design load. So I will begin by beams. So we have different common beam section, and number one, you have the singly reinforced beam and doubly reinforced beam. Why are we calling this one a singly reinforced beam? It is because the reinforcement is provided on the tension part only. So this is the tension part. The tension always occurs at the bottom of a beam. So that is where we provide the reinforcement bar or rebar. So that is it. And then we have the doubly reinforced beam. So for doubly reinforced beam, we reinforce on top and bottom It means on the tension part and on the compression part. So we know that concrete is good in compression and weak in tension. So when we provide reinforcement, we provide on the bottom part of the beam, which is in tension, and the top part is in compression. So this one is doubly reinforced beam because the reinforcement has been provided on both compression and tension part. Then we come to T section beam. So for T section beam, it supports both sides. As you can see, it supports on the left, on the right, and on the left. That's why you call it a T beam. So this one can be a floor. So it can support on that part, half of that part, and half of the other part. And then you have the L section. As you can see, the L section, this is how it looks. So those are the common beam section. So we will begin by designing singly reinforced beam. So let's begin by singly reinforced beam design. So we know that beam fail due to excessive bending or shear, and also excessive deflection must be avoided. And in limit state design, we have two types of limit state design, that is ultimate state design and serviceability. So in ultimate state design, you design a structure to prevent a structure from collapsing or from failing. And then for serviceability, you design a structure for the comfort of the person living in that structure or using that structure. So bending and shear, it is categorized as ultimate state, and deflection is serviceability. So we proceed to design consideration. We have bending, shear, and deflection. So I will begin by bending. As you can see, this is a loaded beam. It is loaded with a UDL W per meter. So this loading, it will cause this beam to sag. It will sag in a curve. As you can see, as it sag, the bottom part of this beam, this bottom part will increase as the outer part decreases. Due to increase in the bottom part, crack develops. These are the cracks. And the bottom part is what we call the tension zone. And the upper part is what we call the compression zone. So when this beam sag this way, it will cause a distance. There will be a variation in distance from the original place. So this distance is what we call deflection. So that is deflection. So we provide reinforcement on the bottom part of this beam to prevent cracking and to prevent excessive bending. I want to talk about under reinforced beam and under reinforced beam analytical. And before I can start talking about under reinforced beam analytical, I want you guys to go and do more research on types of failure and beam section classification. I think I made this video sometimes back, and I will copy the link in comment section so that you may go through the video so that you may be able to know what what are the types of failure and beam section classification. So we have balanced design case, we have underbalanced design case, and over reinforcement case. So those are the three types of failure and beam section classification. So let's now go to under reinforced beam analytical. So for this case, this is the beam section and this is the stress diagram. So this beam section, it has a depth D. So this is the depth of reinforcement from the top to the middle of the reinforcement, and H is the overall depth. So this is the stress diagram as a result of under reinforced beam analytical. So there is a lot of derivation in this case, but I have just skipped the derivation so that I can give you the formulas which are very important in designing singly reinforced beam. So these are the formulas. Before I go to formulas, we have this Z, we have ZFST and FCC. So FST is the force. FST is the force in steel tension. And FCC is the force in concrete compression. So from this section, we will have these formulas. Z, which is the lever arm, is given by this formula. D into bracket 0.5 plus 0.25 minus K over 0.9. You close the bracket, then you raise it to a half. So this equation is found in BS 8110 and it is equation 3.13, whereby K is equal to M over FCU BD square. So Z should not exceed 0.95 D in order to give a reasonable concrete area in compression. If Z exceeds 0.95 D, then you should use 0.95 D as Z. And then the area of steel is given by this formula, M over 0.87 FYZ. So this is equation in BS 8110, equation 3.12. So this equation, which is area of steel, is equal to M over 0.87 FYZ, which is equation 3.12 in BS 8110. It can only be used to determine area of steel if, number one, M is less than MU, and MU is given by 0.156 FCU BD square. And then number two, K is less or equal to K prime, where K is equal to M over FCU BD square, and K prime is equal to MU over FCU BD square, where M is greater than MU, the designer, of course is you, has the option to either increase the section size, this is the section size of a beam, or design a doubly reinforced section, which I will discuss later in this topic. So I want to end there, and for those who have not subscribed to this channel, please subscribe and hit the notification bell so that you may be the first person to be notified when I upload a video. Don't miss my next session, of which I will start designing a singly reinforced beam. Thank you for your time, and we meet again in my next session.